Hello, hello. Hope everybody's doing okay out there. This is the lecture for April 14th, 2021. I want to spend some time talking a little bit about an example in Green's theorem, just applying it, and then moving on to what we do in the case of situations that aren't necessarily confined to two-dimensional space. Remember, Green's theorem told us what to do if we have a non-conservative vector field that we want to compute a work integral for, and we happen to have a two-dimensional vector field, i.e., we are confined to two-dimensional space. Well, what in the world are we going to do if we happen to be in three-dimensional space? What then? What then? Well, it turns out in order to understand that fully, we have to get into the concept of surfaces themselves. We're no longer going to be just interested in parametrizing curves, but we're going to be interested in actually parametrizing surfaces, okay? So it turns out we're going to look at something called not line integrals or curve integrals, as I like to call them, but surface integrals. And parametrizing surfaces isn't necessarily more complicated than parametrizing curves. It just ramps up the dimensionality. So when we parametrize a curve, we have one parameter, namely t. So it's kind of like a one-dimensional parameter that gives us kind of a curve in three-dimensional space. Okay? It moves us along the curve in three-dimensional space potentially. But now what we're going to do, if we want to move around on a surface instead of just on a curve, we actually need not just one parameter, but two. So when we parametrize a surface, we need two parameters. Okay, so that's a little bit more complicated, but given how much experience we've had with curves, it shouldn't be that big of a deal to ramp up the dimensionality a little bit. I think you'll see what I mean. But before we get into that, let's talk about Green's theorem, shall we? So here I'm going to try to use Apple Note here just to switch it up a little bit and see how that goes. Okay. So here we go. Okay. So actually this was me just messing around with things. I need to erase this. Sorry about that. And we will get going here. Okay. So do you remember what Green's theorem actually says? Well, talks about what we do in the case of having a two-dimensional vector field. Oh, wait. Erase this too. Sorry about that. Okay, so we have a two-dimensional vector field, and we are going around a curve on that two-dimensional vector field. Okay, going around that curve, and that two-dimensional vector field is operating upon us. We want to see how much work is done as that vector field moves us along that curve. Okay, so the picture that we had was something like this. So here was our curve. Like this. Remember, we had to have the positive orientation, and the region R was what is inside of that curve. So remember, Green's theorem only applies to this situation here specifically. Okay, so what does Green's theorem say? Well, let's take a look. It was the integral around the curve with positive orientation, f dotted with dr is equal to what? The double integral over the region bounded by C, q sub x minus p sub y dA, where what? F of xy is a two-dimensional vector field, and the coordinate functions were p of xy and q of xy. And we talked specifically about what this meant, in various contexts. We actually talked about how this could be used to compute the areas of regions. And I showed you that picture of a planometer. There's been lots of ink spilt on the planometer concept, but all of it is rooted in what Green's theorem is saying here. And please don't forget that you can also write these line integrals this way, okay? Integral over C, P dx plus Q dy, if you will recall, okay? So let's do an example here, just to kind of get our feet wet and remember what we did last time. So what about this? Let's compute the following. So compute what? The integral over C, okay, and this curve is going to have positive orientation all the way around, x squared minus y squared dx plus 2xy dy, okay? And what's C? C is given by the cardioid r equal to 1 plus cosine of theta. R is equal to 1 plus cosine of theta. You may or may not recall that that's a cardioid, okay? Let's kind of draw a picture of this just to kind of refresh our memory. Okay, think about it. If you plug in, remember this thing is parametrized kind of in the polar coordinates here, okay? So if theta is 0, cosine is 1, and so the radius is 2, okay? And then what happens? Well, as theta goes to pi over 2, this thing goes down to 1. Okay, so the radius has decreased to 1 at that point. And then what happens? As theta increases to pi, cosine of theta decreases to -1, which would make the radius 0. So this thing kind of goes like this, and decreases to 0 like that, okay? And then what happens? Well, once we go past pi, radius is back positive again. Okay, I think it's going to go out to a length of 1, and we get this kind of sideways cardioid looking thing. So that's our curve C. Okay, that is our curve C in this particular case. Okay, so that's an interesting little reminder. Remember, cardioid situation. R equal to 1 plus or minus cosine of theta is a cardioid. R equal to 1 plus or minus sine of theta is a cardioid as well. Okay, and you can get some other interesting things by changing the 1 to other numbers and changing the things sitting in front of sine and cosine to other numbers also. Okay. Well, how is this curve going to be parametrized? So let's think about this. Well, it's going to be x equal to r cosine of theta. Yes. So it's r cosine of theta. And in this particular case, what's r? Well, r is 1 plus cosine of theta. And then it's cosine of theta. So there's x. And then similarly, y is equal to r sine of theta. So this would be 1 plus cosine of theta. That's what r is. Sine of theta. And theta is going between 0 and 2 pi. All right? Okay. Interesting. Okay, so that's how the thing would be parametrized if indeed we wanted to go ahead and compute this line integral in the old-fashioned way, if you will. Okay, we could actually plug in what x and y are. We could figure out what dx is, and we would integrate everything in terms of theta, if you will recall. Okay, so what do we do in the case of trying to instead compute things around this curve right here? And what would we do in the case of just trying to compute things around this curve right here? Well, we know that by Green's theorem, this can be reduced to simply just doing the double integral over r of what? Well, you're going to look at the second coordinate function here. So this is our q, okay? So this is q. And this guy right here is p. And you would go q sub x minus p sub y. So q sub x minus p sub y. dA. Okay, so let's see what happens here. So this is equal to the double integral over the region R of what? What's Q sub X? Well, that's 2y. Okay. And then it's going to be, okay, what in the world is P sub y? Well, that's negative 2y. So 2y minus negative 2y is 2y plus 2y dA. Okay, this is already looking better. I'm telling you, it would have been fairly unpleasant to actually plug in what x and y were in terms of theta and try to compute this work integral in the old-fashioned way. Okay. So let's think about this here. What would be the most convenient way to compute this thing, I wonder? Okay, what would be the most convenient way to compute this double integral over this region? Well, it stands to reason that using polar coordinates might be a good idea, don't you see? Okay, so in this particular case, I have up here, this of course is just 4y. And if I convert to polar coordinates, hey, what's the deal going to be? Well, to intercept that entire region R, my theta is going to have to go from 0 to 2 pi. Okay, so that's d theta. Okay. And then what else? So theta goes between 0 and 2 pi. And then what else? Well, wherever theta is, R goes between 0 and 1 minus theta. So wherever theta is, let's think about this. Okay, so wherever theta happens to be, okay, so if this is a particular angle theta, then R is going to start at 0 and go out, out, out till it actually hits the curve itself. But that curve is given by R equal to 1 plus cosine of theta, right? It's the cardioid after all. Okay, R equal to 1 plus cosine of theta. Okay, so fix any theta, R travels between 0 and that curve, R equal to 1 plus cosine of theta. That's what's going to intercept that entire region. Okay, so let's write that down. R itself goes between 0 and 1 plus cosine of theta. Okay, so that's dr. Now remember, when you convert to polar coordinates, it's r dr d theta, yes? And what does 4y become? Well, it's going to be 4, okay, what is y? What is y in the polar coordinates? Well, y is r sine of theta. Okay, there we go. Okay, so on the whole, let's kind of write down what we have here. This is going to be the integral from 0 to 2 pi, the integral from 0 to 1 plus cosine of theta. And why not? Let's sort of pull the 4 out here, and it's going to be r squared sine of theta, dr d theta. Okay. Well, okay, what now? What now? Well, let's see. The antiderivative of r squared is 1/3 r cubed. Yes, 1/3 r cubed. Okay, so this is going to be 4/3. I'll kind of pull out the 1/3 here. R cubed, and you plug in r equal to 1 plus cosine theta and r equal to 0. And what you're going to get is the integral from 0 to 2 pi. It's going to be r cubed, which is 1 plus cosine of theta cubed times sine theta d theta. Okay? Well, that's interesting. Seems to me that this thing is kind of ripe for a u substitution of some kind, don't you see? If I put u equal to 1 plus cosine of theta, for instance, then du is just minus sine theta d theta, i.e. negative du is equal to sine theta d theta, which is exactly what we see right here. So that would be negative du. And of course, this guy right here would be u. And we'll kind of adjust our limits of integration accordingly. So it's going to be equal to negative 4/3. The integral from somewhere to somewhere, we'll figure that out in just a second. It's going to be u cubed du. And now what about what u goes between? Well, if I plug in theta equal to 0, u is 2 at the bottom. And if I plug in theta equal to 2 pi, cosine of 2 pi is 1. It's the same value as it was before. It's 0. So it's going to be the integral from 2 to 2. And now don't you see what is the value of this thing end up being? Well, 0. 0. Okay. Just to emphasize that, we circle it with red. Okay, so the answer to that thing ends up being 0, which makes me kind of wonder, if we went back to the beginning, is this thing actually a conservative vector field? Well, no, it's not. If it were a conservative vector field, it turns out that this thing right here would have been 0, q of x minus p of y. Turns out that right there is like the third coordinate of the curl of this vector, okay? And so that would have been 0. So it just so happens that this work integral ends up being 0. There's nothing going on here in terms of the vector field itself being conservative, okay? That's kind of an interesting example here, okay? Just an interesting application of Green's theorem. Hopefully that's kind of helpful. All right, so let's move on. Okay, let's move on to parametric surfaces here. Okay, so parametric surfaces. This is section 15. This is section 15.5. Yes, section 15.5 on parametric surfaces. Okay, 15.5. Wanted to make sure I wasn't quoting the wrong section. Parametric surfaces. Okay. And the goal here in this section is to parametrize, parametrize surfaces and no longer just curves. Okay. Now here's the thing. When we did curves, we needed only one parameter. We only needed one parameter. And we called that t, if you will. Okay. The reason that we can parametrize curves with just a single parameter is because when you walk along a curve, it's basically like one-dimensional. Like if you were walking around on a curve, you look down, you would say, oh man, I'm walking around on like a one-dimensional thing. Okay. Even though you might be moving around in three-dimensional space, locally, if you look down at that thing, you would say to yourself, oh, that thing is basically behaving like something in one-dimensional space. A surface, if you walk around on a surface, don't you see? If you're walking around on a surface and you look down, kind of like the surface of the earth, you look down on that surface, you say to yourself, actually, this looks kind of like a two-dimensional thing right here that I'm walking around on, okay? So a surface requires two parameters. And for those two parameters, we often use u and v, okay? And just like over here, we kind of parametrize the curve with r of t, and we, without apology, kind of used vector notation just because it's convenient to do that, to think of points on the curve r of t as vectors emanating from the origin so that we can use all of our vector prowess, okay? We do the same thing with surfaces, except we don't have a vector that just depends on one variable. Our vector now is going to depend on two variables, okay? It's going to depend on two variables, which is very, very interesting. Okay, so here's kind of a picture of what we have in our mind, okay? So, I mean, here's kind of our surface, like this, okay? And we are in three-dimensional space, okay, like this. And again, if you were walking around on this surface, if you were walking around on this surface, you would feel like the stuff you were looking down at was two-dimensional, namely the surface of, like the surface itself, the surface of the surface. okay? So you might be at like this point on the surface. And what we've done here is we've basically created a vector that represents this point on the surface. Okay, so this point is basically given by the vector r of uv. Okay, r of uv. Okay. Now again, just to remind you, you have x, you have y, and you have z sitting here. U and v are a couple of other variables here that x, y, and z could all depend on in theory. So the way that we parametrize things, r of uv is equal to, okay, you're going to have an x coordinate function, x of uv. You're going to have a y coordinate function, y of uv. And you're going to have a z coordinate function, z of uv. Okay. And then, of course, remember, like over here in the curve case, I could do things like, say, r prime of t, and that would be sort of like that would have been the tangent vector that kind of showed us how we were moving around on the curve. It pointed us in the direction of motion for the particle on the curve itself. Well, here, for crying out loud, I don't just have one derivative anymore. Now I have a couple of derivatives. I have r sub u and I have r sub v. I have the partial derivatives of these things. Okay. So r sub u, I mean, what r sub u is going to do is it's going to feel what's happening on this surface, right? So r sub u might be, you know, something like this vector right here. And r sub v, you know, might be something like this vector. So r sub v might be like this. And of course, you know, r sub u, what in the world am I talking about? Well, r sub u is going to be the u derivative of x, the u derivative of y, and the u derivative of z. And r sub v, that's going to be the v derivative of x, the v derivative of y, and the v derivative of z. Okay? And so these two vectors, r sub u and r sub v, kind of feel what's happening surface-wise at that point, r at uv. Okay? So letting u and v move around moves us around on the surface itself. And then r sub u, the u derivative and the v derivative of r, feel what's happening at the surface at that point. And it can kind of tell us locally what's happening there. And it's going to tell us stuff about the tangent plane at that point as well. Okay. So hopefully that kind of makes sense. Let's look at an example here. So example, look at this guy. So r of u and v equal to 2 cosine of u. All right. V in the second coordinate and 2 sine of u. Okay. And let's just let u and v do their thing. I'm not even going to give you a range for u and v. Well, so what is this? So what is it? What is this? What is this? Well, if you think about the x and the y, or the x and the z coordinates actually, okay, and you think about what you're going to get if u moves around, you are going to get a circle of radius 2. Okay, you are going to get a circle of radius 2. Okay, so you get a circle of radius 2. So so by letting, so let me just say, if u moves, the x and z sketch a circle of radius 2 centered at the origin, or yeah, centered at the origin. Okay, then what in the world is going on with this middle coordinate here, v? Well, if I let V move around, okay, so Y is equal to V. So remember in X, in terms of what X and Z are doing, as U moves around, it just sketches out these circles of radius 2. And then V, that's what the Y coordinate is. That's just going to move us along the Y axis. Okay. And so as V moves and U moves, you just keep getting these circles of radius 2, and V moves us along on the Y axis. Don't you see what you're going to get here? So this guy, so let me just circle this again. This guy just moves these circles around the y-axis. Okay, moves these circles like rings around on the y-axis. Okay, circles themselves just get kind of moved around on the y-axis everywhere. So don't you see what kind of surface this is going to be? It's going to look like this. Okay, it's going to be basically just a tube with the y-axis right in the middle. Okay, so let me just kind of try to draw this. Okay, so here's these tubes. And let me try to very judiciously draw this. So there's the z-axis, right? Here's the y-axis. Okay, so here's z, here's y, and then x is going to come out like this. Okay, so here's x, and of course, what do the little cross sections look like? Well, all of the cross sections, as it pertains to x and z, are just going to be these little circles of radius 2. This is 2 in this direction. Okay, if it goes out here and kind of hits right here, this is 2 in this direction, like this. Okay, as far as x and z are concerned, just sketches out those things. So let me just say, kind of moving us around on these circles is the parameter u. Okay, and then moving us in this direction along, right? So that's kind of like the parameter v. Okay, so these little circles get strung like rings around the y-axis. Okay, so that's how we would parametrize that particular surface. Okay, look, this time the parametrization was actually given to us, and it was just up to us to actually identify what this surface was. And it turns out it's a cylinder of radius 2 with the y-axis running right through the middle of it. It's a circular cylinder of radius 2 with the y-axis running right through the middle of it all. Okay. All right. Okay, so that's cool stuff. Let's think about one or two other things. So what about a surface of revolution? Okay. Probably remember doing surfaces of revolution. Surfaces of revolution. Okay. Remember, like we would do things where we would revolve around like the X or the Y axis in Calc 2. We would compute the volume of the resulting solids when we would do that. Well, not solids, but the volume of the solid itself, if we kind of filled in the inside of those things. Okay. So, so for instance, let's just imagine that we had this. Okay, so let me just kind of draw a picture. Okay, so here's A, here's B. Okay, here is the curve y equal to f of x. Okay, and don't you remember we would like revolve this thing around. Okay. Okay, so then I wish I wouldn't have drawn such a complicated thing like this. But that's how this surface looks that we end up getting. Okay. Now, what do we get every time, as I kind of move around on the x-axis here, so this is, of course, the y-axis. as we move around on the x-axis, every time we get a circle, it's kind of like the washer method for this surfaces of revolution. So this time we revolved around the x-axis. Okay, what is the radius of this this circle? Well, the radius, if I'm at a particular x value, okay, the radius of this thing, r, is equal to f of x, okay? So the radius of that thing is equal to f of x, okay? And then here's the thing, if I want to somehow get all of this surface, all of it, okay, all the way around, well, we know how to parametrize a circle, and we know how to parametrize a circle, okay? That's just going to involve the sine and the cosine functions, okay? So if you think about it for a minute, this guy right here, you know, how would you parametrize that thing? Well, it's basically going to be, you take the radius, cosine of something, and then you take the radius, sine of something, sine of the angle, then that will kind of move us around that particular circle right there, okay? So, hey, this is interesting. So where is this circle right here, where does this circle live? So this thing, this circle has the x-axis. So this thing is has x-axis through the center. Okay. Well, if that's true, then it's kind of like the situation that we just had, isn't it? Okay. Where we had one thing that kind of moves us along. And then up here, it was the y-axis that sort of moved us along. Well, down here, it's going to be like the x-axis that's going to move us along. So let's try to parametrize this thing. So it's going to be r of u and v, okay? And just kind of copying what happened up here, let's see, v corresponded to the thing that kind of moved us along. Okay, so it seems like in this case, x is doing that, right? So we'll put v as our x coordinate, okay? And before, what we did is for every value of v, we ended up getting this circle of radius 2, okay? So whatever v is, whatever v happens to be, remember, so our x coordinate is v. We're kind of replacing x with v itself. Wherever our x coordinate is, which is also v, we get a radius, which is going to be f of v. Okay, so this is going to be f of v. Okay, that's the radius. And then we'll say, I can either put it cosine or sine. It doesn't really matter. I'll just use cosine. Okay, so this is cosine of v, or cosine of u, actually. U is the thing that's going to move us around. F of v is the fixed radius. Okay, and then same radius, sine of u. Okay, and so u is going to be the thing that kind of moves us around that thing right there. So in this particular case, what's going on? What would be the range of v values? Well, you would have a equal to or less than v equal to or less than b. And then what would u have to go between to kind of get us to move around all of those green circles? Okay, so once again, I'm just reminding you, x we kind of set equal to v in this particular case, okay? And then we have, you know, this thing is then equal to f of v. And the parameter u is what moves us around those circles, okay? So what are the values of u? Well, 0, you don't have to write this down, but we'll go ahead and do that. 0 equal to or less than u equal to or less than 2 pi, just so that we don't like wrap around the surface twice or something like that, okay? And there you have a parametrization of a surface of revolution. You can kind of see how you do that. You just think about, okay, what's the axis that's going to like move me around? Okay, in this case, you kind of imagine that the z-axis is coming out in this direction, okay? So you imagine which of the variables is going to move you around. You set that equal to one of the parameters. And then you let the other parameter kind of move you around the surface itself on one of those circles. And the radius depends on where you are as you move along the axis, okay? So that's kind of cool. We're able to parametrize that particular thing. And it wasn't all that unlike this example right up here, okay? All right. I think that's good for now. I'm going to sort of stop right there. Next time I'm going to, on Friday, I'm going to talk about tangent planes a little bit. Remember up here, I mentioned that will involve the u and the v derivatives of the parametrized surface. That will tell us what's going on locally at these points on the surface. And we will actually use that to tell us information like things about the tangent plane itself, or things about the surface area of the surface itself. We're going to have a lot of power now that we have moved beyond parametrization of curves, and we've moved into the realm of parametrizing surfaces themselves. And then eventually we're going to see some really cool closing applications for the entire calc sequence involving parametrized surfaces, and not line integrals, but surface integrals. Okay? All right. Well, I'm going to go ahead and stop right there for now. Hope you're having a good day, and I will see you on Friday.